no nation which expects to be the leader of other nations can expect to stay behind in this race for space.
Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and help us out on Patreon if you can. We appreciate you. NASA has awarded a Next Step 2 Appendix P Sustaining Lunar Development contract to Blue Origin. Under this contract, Blue Origin and its national team partners will develop and fly both a lunar lander that can make a precision landing anywhere on the moon's surface and a cislunar transporter to keep lunar missions supplied. Let's look at these two in depth. The lander is called Blue Moon and was unveiled by Jeff Bezos on May 9, 2019. It is designed to deliver a variety of payloads to the lunar surface. Here are some key points about the Blue Moon lunar lander. Payload capacity. Blue Moon is designed to land up to 4.5 metric tons of cargo on the lunar surface in its basic version. A stretched tank variant is designed to carry a human-rated ascent stage, potentially landing humans on the moon. Propulsion. The lander uses Blue Origin's BE-7 engine, which runs on liquid hydrogen and liquid oxygen. The choice of this fuel is strategic, as it aligns with Blue Origin's long-term vision of utilizing in situ lunar resources. Future lunar explorers could potentially extract water ice from the lunar regolith, which can be processed into hydrogen and oxygen. Precision landing. Blue Moon is designed to perform a very precise landing with an autonomous navigation system. This system uses machine learning technologies to accurately land within meters of its target location. Infrastructure delivery. Apart from carrying rovers and other scientific equipment, Blue Moon could also help deploy infrastructure like power stations and other resources for human habitation and communication systems in advance of a human landing. Scientific research. Blue Moon could play a crucial role in improving our scientific understanding of the moon by providing transport for instruments that could study the lunar geology, environment, and potential resources. The Blue Moon lander design began in 2016 and was first announced to the public in March of 2017. A mock-up was unveiled in May of 2019 by Jeff Bezos. The lander will be sent to the moon using the BE-3U rocket engine. The BE-3U is an open expander cycle cryogenic hydrogen and oxygen rocket engine. Two of them will be used on the second stage of the New Glenn rocket. The New Glenn first stage will use the BE-4 rocket engines, as will the Vulcan Centaur rocket system. The BE-4 uses liquid methane and oxygen propellant and is an oxygen-rich stage combustion rocket engine with a thrust of around 2.4 meganewtons. The BE-4 has been discussed in many lessons. The thrust of the BE-3U engines on the second stage should be about 710 kilonewtons. And these engines can throttle down to just 89 kilonewtons, or 12.5% of full thrust. Low throttling is a benefit of expander cycle engines. These engines are somewhat derived from the BE-3, which is used to fly the New Shepard suborbital spacecraft, though there are some important differences. The BE-3PM used on the New Glenn rockets are tap-off cycle rocket engines, running a pipe from the combustion chamber to provide power to the turbopump. One of these had a malfunction back in 2022 when the New Shepard 3, carrying the uncrewed RSS H.G. Wells capsule, suffered what Blue Origin calls an uncontained engine failure, resulting in an in-flight abort. The New Shepard 3 was lost, but the H.G. Wells landed without problems. Accidents like these are expected in spaceflight development. In this case, there was a thermostructural failure of the engine nozzle. This was caused by some design changes in the engine's boundary layer cooling system. Rocket nozzles can be cooled in many ways. The simplest is radiative cooling, where we just allow the heat to disappear to the outside environment. Regenerative cooling is a method where the engine's fuel or oxidizer is circulated around the walls of the combustion chamber and the nozzle, absorbing heat and keeping these components cool, before being injected into the combustion chamber. Boundary layer cooling is a different principle and refers to a layer of cooler combustion gas that normally forms along the interior walls of the combustion chamber and nozzle during operation. This cooler gas, relative to the primary combustion gases, helps insulate the walls from the extremely high temperatures in the primary flow, providing some level of cooling. This phenomenon is a natural result of the gas flow characteristics and doesn't require a specific design like regenerative cooling does. Its effects, however, must always be considered in the design and operation of rocket engines. By itself, natural boundary layer cooling is usually insufficient to prevent overheating in high-performance engines. Supplemented boundary layer cooling, also known as film cooling, is a technique also used in rocket engine design. It's used to further protect the rocket nozzle and combustion chamber walls by injecting some amount of the rocket propellant into the combustion chamber in such a way that it forms a protective film along the walls of the chamber and nozzle. This film of relatively cooler gas insulates the walls from the hotter combustion gases in the main flow, reducing the heat transfer to the walls. Implementation of film cooling must be carefully designed to avoid disrupting the efficiency of the combustion process. If not properly managed, the cool boundary layer can interfere with the combustion of the primary flow, reducing the engine's performance. Or the flow from the combustion chamber can cause hot streaks. In the case of New Shepard 3, a recovered nozzle fragment shown here demonstrated that a persistent hot streak had formed due to a failure of the modified boundary layer cooling system, and this resulted in the loss of that vehicle. Now back to the BE-3U and the Blue Moon lander. Remember that the BE-3U is an expander cycle, not a tap-off cycle, like the BE-3PM. The BE-3U also has an extendable nozzle, like those used by other rocket engines over the years. The Blue Moon lander itself will be brought down onto the lunar surface by the BE or Blue Engine 7. The BE-7 is a dual expander cycle rocket engine, meaning there is one expander circuit for the fuel and another one for the oxidizer. This design can be very efficient, and the BE-7 is expected to have a specific impulse of 453 seconds, making it just a little less efficient than the Space Shuttle main engines, which is still behind the king of chemical rocket engine efficiency, the RL-10B2, used on the Delta cryogenic second stage, which achieved 465.5 seconds. But still very respectable. The BE-7 will produce a thrust of 40 kilonewtons. Now let's look at what that means. We often just divide kilonewtons by 10 and estimate tons of thrust, and that's okay for a rough estimate on Earth, but could lead to errors down the road. 40 kilonewtons is 40,000 newtons. A newton is 1 kilogram meter per second squared. A 1 kilogram mass in your hand on Earth, being pulled toward the center of the Earth with 1 g of normal Earth gravity, would generate a force or weight of 1 times 9.8 meters per second squared, so 9.8 newtons of weight are felt by your hand. If you reduce the mass to about 102 grams, on the other hand, you would feel 1 newton of force. For my American friends, 102 grams would be almost exactly 18 quarters, $4.50 worth. A 40,000 newton thrust rocket engine on Earth could hover about 4,081 kilograms of mass against gravity. But gravity on the Moon is less than what it is on Earth, only 1.622 meters per second squared, in fact. So a 40,000 newton thrust rocket engine on the Moon could hover 40,000 divided by 1.622 gives us 24,661 kilograms. And that makes sense. The engine can lift about 6 times as much on the Moon, because gravity there is 1/6 of what it is on Earth. The Blue Origin lander, called the Integrated Lander Vehicle, will have 3 main components. An in-space transfer element, built by Northrop Grumman, to get us to the Moon. A descent element, which is a variant of the Blue Moon lander, to get us to the surface. And an ascent element, which will be built by Lockheed Martin to get us back home. This design was supposed to land as early as 2023, but it's not looking good for that date. Now they are looking at 2026 and beyond. The Blue Origin cislunar transporter will be a kind of automated tanker ship, using technology similar to the in-space transfer element, and will carry propellant from low Earth orbit to the near rectilinear halo orbit around the Moon, where the lander will be located. Cislunar space generally refers to all the space within the Moon's orbit, and a cislunar transporter would presumably refer to a spacecraft designed to transport payloads or passengers between Earth and various points within this space, such as lunar orbit and stable points like Lagrange points. or to what is called a near rectilinear halo orbit. A near rectilinear halo orbit is a specific type of highly elliptical orbit around the Moon that brings a spacecraft very close to the lunar North Pole at its closest point and takes it far away from the Moon, nearly as far as the L1 Lagrange point at its furthest point. This type of orbit has been selected for the Lunar Gateway, a small space station that is planned to be built by NASA in collaboration with international partners for the Artemis program. Not everyone is a fan of the Lunar Gateway. Dr. Robert Zubrin believes it is a mistake to waste the Delta V to dock here on the way to and from the Moon, and likes to call it the Lunar Toll Booth. There are some advantages of being in a near rectilinear halo orbit, such as orbit stability. The NRHO is a dynamically unstable orbit, but has the advantage of requiring minimal fuel for station keeping due to the gravitational influence of the Earth. There's also solar power. The spacecraft in an NRHO has nearly continuous solar power availability. And visibility. There is an almost continuous line of sight between the orbiting object and the Earth, which is important for communication. Accessibility. This orbit provides good access to lunar resources, and it's especially suited for missions aiming for the lunar South Pole, a region of significant scientific interest, due in large part to the presence of water ice in the massive Shackleton and some of the other craters. And it is also beneficial for missions going beyond the Moon. Having the gateway at the NRHO serves as an efficient staging post for missions to Mars and other destinations in the solar system, acting as a waypoint where ships can exchange personnel and resources before heading out. While an NRHO provides many advantages for lunar missions and potential deep space missions, planning and executing missions in this complex orbit requires careful consideration and advanced technologies for precise navigation and control. Blue Origin's national team partners include Lockheed Martin, Draper, Boeing, Astrobotic, and Honeybee Robotics. Lockheed Martin is a principal partner and has over 50 years of experience in space systems operations. Draper will provide guidance, navigation, and control systems, as well as training and simulation. Boeing will contribute the docking system. Astrobotic will handle cargo accommodations, and Honeybee Robotics will provide cargo offloading capabilities. This system, however, was not NASA's choice for the first award. In April 2021, NASA chose SpaceX for its first human landing system program. Blue Origin and Dynetics, the two losing bidders in that competition, protested the award to the Government Accountability Office. Their protest was rejected, but Blue Origin went on to file suit in the Court of Federal Claims, eventually losing the case. Both Dynetics and Blue Origin, however, did receive further funding from NASA's Next Space Technologies for Exploration Partnerships effort to mature their needed technologies, such as engines for their landers. Then NASA announced an initiative called Sustaining Lunar Development, or SLD. This initiative was an effort to ensure competition in the overall HLS effort. A second-place award, if you will, addressing concerns raised by some members of Congress that it would be a mistake to count on any one vendor, even SpaceX. So SpaceX was excluded from the SLD competition, leaving Dynetics and Blue Origin. The Dynetics Alpaca lander had a very unique design, which allowed much easier access to the lunar surface than either the Blue Moon lander or the Starship. But at an event at NASA headquarters on May 19, 2023, NASA Administrator Bill Nelson announced that the agency had chosen Blue Origin to lead this second team. NASA officials did not immediately disclose the rationale for selecting Blue Origin over Dynetics, but did say their reasoning will be released in a separate source selection statement. The contract includes a demonstration landing on Artemis 5, currently scheduled for no earlier than late 2029, as well as an uncrewed test flight of the lander about 1 year earlier. Artemis 5 will be the third crewed landing of the Artemis lunar exploration campaign, after the Artemis 3 and 4 missions that will use SpaceX's Starship. SpaceX has already been working on its contract to develop and land a lunar Starship. The value of the fixed-price award to Blue Origin is $3.4 billion. John Koulouris is the Blue Origin program manager for the effort, and he said at a recent briefing that Blue Origin plans to invest much more than that amount to develop the lander. NASA also exercised what it called Option B in November, granting SpaceX an additional $1.15 billion, bringing the total value of SpaceX's HLS budget to more than $4 billion. Both SpaceX's Starship and Blue Origin's Blue Moon will eventually compete for missions after Artemis V, an arrangement similar to what NASA currently uses for cargo and crew missions to the space station. The Blue Moon lander is a revised version of earlier designs released by the company. The lander is now 16 meters tall and designed to fit inside the 7-meter payload fairing of Blue Origin's New Glenn rocket. It has a dry mass of 16 metric tons and a wet mass of more than 45 metric tons when it's been filled with its liquid hydrogen and oxygen propellants. Lower performing but more easily storable propellants, such as hydrazine and nitrogen tetroxide, were used in the only human-rated lunar landers to make it to the moon so far. Hypergolics were favored for the Apollo missions because of the simplicity of hypergolic engines. Open the valves and go bye-bye, which is why they are still preferred for reaction control systems and launch abort engines. But hydrogen and oxygen engines are more efficient, and propellant can be made on the moon using just water and electricity. Working with cryogenic propellants, like liquid hydrogen and oxygen, does create a boil-off problem during long mission timelines. Keeping those super cold propellants from boiling off is a key enabling technology for the Blue Moon lander, and Blue Origin has been working hard on this problem. According to Mr. Koulouris, the company has been internally funding zero boil-off technology for some time. This technology will use a cryocooler that operates at or below a temperature of 20 Kelvin. A cryocooler is based on Stirling engine technology and is fully described in this lesson, but briefly. A Stirling engine is a type of heat engine that operates by cyclic compression and expansion of air or other gas. This gas is called the working fluid, and there must be a temperature differential between the two ends. A Stirling engine will not function unless one end is colder than the other end. This device results in the conversion of heat energy into mechanical work. A Stirling cycle involves all four main operations in a thermodynamic cycle: compression, heating, expansion, and cooling. When this principle is applied to create a cryocooler, the Stirling cycle operates in reverse, also known as the reverse Stirling cycle. This process is used to cool down an environment or material to cryogenic temperatures. Here's how it works. Compression. In the high-pressure phase of the cycle, the working gas, usually helium, is compressed in the compression space. This process increases the temperature of the working gas. Heat exchange. The hot, high-pressure gas then flows through a regenerator, which stores the heat, before entering the cold expansion space. In the expansion phase, the gas does work on the piston or displacer and cools even further. Cooling. Finally, the cold gas returns to the regenerator, picking up the stored heat before being recompressed. So in cryocooler mode, an electric motor moves the Stirling engine to pull heat away from your cryogenic tanks and expel it out into the environment. In generator mode, heat passing through the Stirling engine creates mechanical movement that is used to power a generator. The key advance of a Stirling cryocooler is its high efficiency and the absence of moving parts in the cold section. This absence of cold moving parts helps reduce vibration and increases the lifetime of the device. It also means that the cryocooler can be scaled down to very small sizes, which has made them especially useful in space applications, for cooling infrared sensors, for instance. The cryocooler on the James Webb Infrared Space Telescope can get those sensors down to 6 Kelvin. Liquid hydrogen needs to be stored at 20 Kelvin to prevent boil-off. Reverse Stirling cryocoolers will be a good choice for this application. One challenge with Stirling cryocoolers is that the gas must be sealed within the device, which can lead to challenges with gas purity and containment over long periods. Also, the efficiency of a Stirling cryocooler depends on having a good heat exchanger and regenerator, which can be challenging to design and manufacture. Like all technologies, Stirling engine-based cryocoolers have their trade-offs, but they represent a valuable tool in the quest for efficient, reliable, and compact cooling to very low temperatures. Blue Origin plans to use this technology to make hydrogen easily storable, so that they can extract hydrogen and oxygen from lunar resources, using it perhaps to start building the orbital habitats that Jeff Bezos dreamed of back in high school, described in this lesson. Besides the Blue Moon version designed to carry astronauts, Blue Origin is planning a cargo version of the lander, which will be able to transport up to 20 metric tons to the lunar surface and return to lunar orbit, or 30 metric tons, on a one-way mission. Blue Origin has also been selected to start development, along with Lockheed Martin, of a nuclear thermal rocket engine, described in this lesson. I know a lot of you are rooting for SpaceX, and I understand. But competition can lead to amazing progress. And if Blue Origin can get New Glenn operating, with a lunar lander, cislunar transporter, and especially a nuclear thermal rocket engine, they could pull ahead of SpaceX, and the first humans back to the moon might be riding this lander. Something to think about. Thanks for listening, and stay safe. At Astra Pro Terra.